Okay, now that we've derived the z-transform, I want to show a couple more analytical examples that are important, and then I want to show a general numerical strategy for designing filters that we can analyze with the z-transform. So first, let me generalize that simple example that I started with. If you remember, what I had was an impulse response that was just 1 at 0 and 1 at 1, and everything else was 0. But we can keep going and say, okay, actually I'm going to make 2b1, I'm going to make 3b1, all the way up to, let's say, the 8th, or index A is 1. And so this gives rise to the difference equation, which would be y of n is equal to x of n plus x of n minus 1 plus x of n minus 2, all the way up to x of n minus a. So before I had a just being 1, but this is a more general equation that I can apply here. Okay, so let me go ahead and analyze this by plugging in a phasor. And so I can do the same kind of stuff I did before, and I end up with this equation here. So if I plug in the phasor e to the I omega n, and then I factor that common term out of each of these, I end up with this difference equation. Now, if you've seen enough math, you'll realize this is actually something called a geometric series. So what it is, it's really z to the 0. So here z is, I should say, it's really z to the 0 plus z to the 1 plus z to the 2 all the way up to z to the a. And yeah, this is something called a geometric series, and what it simplifies to, oh, and also I should say z here, of course, is equal to e to the negative I omega. All right, so this is, I'm doing the special case here, but the general z-transform, it would look like this. Okay, and so the formula for the geometric series turns this into a fraction. And what we're going to have here is that, let me just focus on the, I already know I'm going to have e to the I omega. Let me just focus on the z-transform of the impulse response here. So I'm just going to write that part of it. So that is going to be, if you go back and derive the formula for geometric series, what you'll see is you'll have a fraction where in the numerator it's 1 minus z to the a plus 1, and the denominator it's 1 minus z. Okay, so that's what I get in general. Actually, though, I want to be a little more specific here. I want to analyze this at unit phasors. So let me go and plug back in my e to the negative I omega. And if I do that, I'll get e to the negative I omega times the quantity plus 1 over 1 minus e to the negative I omega. All right, so this is just the formula for the geometric series. It's not that difficult to derive, but it's beyond the scope of the video. I'll drop a link in the notes at the end. Okay, so what I would like to do, again, is try to turn this into an expression that's just the canonical form of a phasor. So amplitude, real number, times the unit phasor. And that'll tell me what this is going to do to the amplitude of a particular phasor that I can involve this impulse response with. And then it will tell me what it will do to the phase separately. And so just like before, I'm going to multiply by fancy ones, but I got to do this a couple times because I got to take care of the numerator and also have to take care of the denominator. So for the numerator, I'm going to multiply by this I'm going to multiply by e to the positive I omega quantity a plus 1 over 2. Okay, so let me do that. So my fancy one is going to have, oh, I copied the wrong thing. I meant to copy this. Okay, so my fancy one is going to be e to the positive I times omega a plus 1 over 2. So that's the trick. I always have whatever the argument is to the exponential over 2. Okay, and if I multiply, oh boy, I have to put this in here for the fraction. Okay, let me fix that up and multiply through. All right, so here's the multiplying by fancy 1. And when we take the denominator and put it over here like this, and then we distribute this through the numerator, we get this. And I've already shown you before that this can be rewritten using Euler's formula, realizing that this minus the negative of it gives me 2i times the sine of what's in there. So I can rewrite this as 2i times the sine of that. Okay, so this is helpful, but I still have to contend with the denominator here. Oop. And, well, it's going to be kind of the same thing. So, okay. Let me once again clean this up, and I'll do the same thing for the denominator. Okay, actually I decided to, when I was taking care of the numerator, I decided to keep this part of the fancy 1 here in the denominator. But then, yeah, I multiplied by that other fancy 1 to take care of the denominator there. I kept this part as a coefficient up here, and then I distributed this part down through the denominator. Ended up with e to the I omega 2 minus e to the negative I omega 2. I can apply the same trick and write that as 2i sine of omega over 2. Then the 2 i's cancel out between the numerator and denominator, and this is my final expression. So I have a unit phasor here, which describes the phase effect of applying this convolution. And then I have this real number here, which describes the magnitude. So let me make a method to plot this, and we'll examine the z-transform. Let's just talk about the magnitude right now. So I'll say def get moving average magnitude, pass along some omegas at which to evaluate it, and I'll say what a is, and I'll just return sine of omega times a plus 1 over 2 over sine of omega over 2. All right, so first let's check this with, okay, maybe I'll say I'll take 100 omegas between 0 and pi. Let's check this with a equals 1. All right, so get moving average omegas, because that's what we started with, right? We started with that filter, which is 2 elements. So h0 equals 1, h1 equals 1, so a equals 1 there. Okay, so we get that plot that we're familiar with there. We do get a warning about a divide by 0, because if you look at this equation, if omega is 0, then sine of 0 is 0. That turns into 0 over 0, which is undefined. But actually, if I go back to my geometric series here, well, there's a special case. If omega is 0, this is just 1 plus 1 plus 1 plus 1, and this formula doesn't really apply anymore. So I did assume here that z was actually not 1. If z is 1, it's even easier, but anyway, okay. But at all the other points, this expression applies. So let's look at a few different examples of a's here. So let's say maybe 4a in, I'll have 1 as a reference. Let's say 1, maybe 5 and 10. So I will do that. Actually, maybe make this little list here. I'll make a legend for us. So let's look at a legend down here. Okay. And so what we see here is as we increase a, as we have a moving average with a larger and larger window, the low-pass filter cuts off lower and lower, although it's got a lot of ripple. This is what they call it. So this is not an awesome low-pass filter. It's a pretty bad one, actually. but you can see at least that the effect of increasing A is to overall only promote the lower frequencies. Oh, and actually I realized, okay, because this can go negative sometimes, that's technically a phase and not a magnitude. For the magnitude, what I really should be doing is taking the absolute value of this. Okay. So the magnitude part is always a non-negative real number. So this is really what you would look at to look at the magnitude. Okay. And so here's where we see these ripples coming up. It's not really a perfect low-pass filter. All right. But I want to actually generalize this even further. by looking at comb filters, which, as you might remember, are filters where we have some spacing, I'll call it big T, so that we have a filter h0 equals 1, ht equals 1, h of 2t equals 1, all the way up to h of, I'll use at again, equals 1. So it's like the moving average, except there are gaps between the successive 1 elements. So I got my headphones on because I want to look at a quick example here. Let's say that t was 100, and I'll make a be 20. So in my impulse response, I'll make enough space for all. It's going to be 21 pulses, so I'll say zeros, a times t plus 1, and I'll say h0 colon t is equal to 1. Okay, that's my comb. Let me just make sure I should have 21, or yeah, 21 I should have 21 ones in there. Okay, there we go. And so now what I'll do is I'll generate a little bit of random noise. Let's say x equal to np.random. Yeah, let's say the sample rate is 44,100. So if I generate a little bit of random noise, let's say maybe 4 seconds of random noise, and then I convolve this with the impulse response, what I'll get is a pitched sound. So if I listen to that, in this case it's a concert A. It should be 441 hertz because the period of the comb filter is 100 samples. Okay, but we can look at this analytically, and it turns out it's very similar. You could go through basically the same derivation here. And what you'll see is at the end of the day, the magnitude, so I'll just write the magnitude of the z-transform in this example is going to be basically the same expression. Let me make sure I put an absolute value around it this time. But instead, I'm going to have a factor of t on the inside. So it'll be sine of omega times t, a plus 1 over 2, and then the denominator have that t as well. Okay, so I took a second and wrote some similar code to what I did before for plotting, and I start with an example here with a equals 10 and then t equals 10. And I'm going to sample a little more on the omega so you can really see this function. You get this nice periodic pattern in the z-transform. So what this is telling us is it promotes, okay, the zero frequency, but also some frequency in its harmonics. And that's exactly what we know the comb filter does, right? It gives rise to a sound that promotes some bass frequency in line with the spacing in the comb, and also all of its harmonics. Now, to see why this makes sense, it probably makes sense to actually switch back instead of having the units here be in radians per sample. If I have it be cycles per sample, so let me divide this by 2 pi. And I'll say, okay, this is going to be cycles per sample. And okay, so now it's a little bit clearer to see why this makes sense in this particular example. Because the spacing of the comb here was 1 every 10 samples. Okay, well that's a frequency of 1 over 10 cycles per sample. So we promote that frequency. We also promote the frequency at twice that, 3 times that, 4 times that, etc. If I make A bigger, so if I use more teeth in the comb, then this effect gets even stronger. And that's what we've heard before with the comb filter. The more teeth we use in the comb, the more the notes pop out against the noise. And then of course, if I change the spacing, let's say that I make the spacing only once every 5. Well, okay, in that case, this is a higher frequency. And so I see that I get these peaks at every 0.2 instead. And if I made it lower, then I get, now I get a peak at 0.05 instead, if my spacing is 20. All right, so now we really can see what a comb filter is doing, and we have an exact analytical expression for the magnitude of the z-transform. Now let me bring this video to a close for a second because I'd actually rather split this up. I'm going to do the filter design part in a separate video. I think this was enough for now, enough math. So let's pause here for a second and I'll continue in the next video.